Today we are going to discuss exercise 9.4. Question number 1 is find the solution of the given differential equation dy upon dx is equal to 1 minus cos x upon 1 plus cos x. Dy upon dx is equal to 1 minus cos x upon 1 plus cos x. Transpose dx to right hand side, we get what dy is equal to 1 minus cos x upon 1 plus cos x dx. So obviously this is variable separable. Integrating both sides, we get integral dy is equal to integral 1 minus cos x divided by 1 plus cos x dx. So integral of 1 with respect to y is y, and on the right hand side, let us simplify this. 1 minus cos x may be written as 1 minus 2 sine square x upon 2 divided by 1 plus, and here in the denominator cos x may be written as 2 cos square x upon 2 minus 1, because cos 2 theta is equal to 1 minus 2 sine square theta, and cos 2 theta is also equal to 2 cos square theta minus 1. So integral 1 minus, if we open up this bracket, we get 1 minus 1 plus 2 sine square x upon 2 divided by 1 plus 2 cos square x upon 2 minus 1 dx. In the numerator, plus 1 and minus 1 cancelled out. In denominator, also plus 1 minus 1 are cancelled out. So we get integral 2 sine square x upon 2 divided by 2 cos square x upon 2 dx. 2 is cancelled by 2 and we get integral tan square x upon 2 dx. Obviously tan square x upon 2 may be written as sec square x upon 2 minus 1 dx. So integrating these two terms with respect to x, sec square x upon 2, integral will be tan x upon 2 divided by 1 upon 2 minus integral of 1 is x plus c. So finally y is equal to tan x upon 2 upon half may be written as 2 tan x upon 2 minus x plus c. So this is the required solution of the given differential equation. Question number 2, dy upon dx is equal to under root 4 minus y square, where y is greater than minus 2 but less than plus 2. So dy upon dx is equal to under root 4 minus y square. Transposing dx to right hand side and under root 4 minus y square to left hand side, 1 upon under root 4 minus y square dy is equal to dx. Now obviously this is a variable separable form of differential equation, so we have to integrate both sides. Integral 1 upon under root 4, which may be written as 2 square minus y square dy is equal to integral 1 dx. So integral of 1 upon under root 2 square minus y square is obviously sine inverse y is equal to x plus c, or y is equal to sine x plus c. So either the required solution may be written as sine inverse y is equal to x plus c, or it may also be written as y is equal to sine x plus c. Now third one is dy upon dx plus y is equal to 1, where y is not equal to 1. So dy upon dx plus y is equal to 1. Transposing y to right hand side, we may write it as dy upon dx is equal to 1 minus y, or dy upon dx is equal to 1 minus y may be written as minus y minus 1, taking minus common. Transposing y minus 1 to left hand side and dx to right hand side, we may write it as 1 upon y minus 1 dy is equal to minus dx. Integrating both sides, integral 1 upon y minus 1 dy is equal to minus integral 1 dx. So obviously integral of 1 upon y minus 1 will be log mod y minus 1 is equal to minus integral of 1 with respect to x is x and plus c constant of integration. This may be written as a solution of the given differential equation, or this may also be written as y minus 1 is equal to e raised to the power minus x plus c, or y minus 1 is equal to, this may also be written as e raised to the power minus x into e raised to the power c. And now here this e raised to the power c is a constant term. So this may also be denoted by some other arbitrary constant like c dash. We may write this as y minus 1 is equal to e raised to the power minus x into c dash, or y is equal to e dash upon e raised to the power x plus 1. And this may also be simplified as e raised to the power x LCM c dash plus e raised to the power x. Transposing e raised to the power x to this side, we may write it as e raised to the power x y is equal to e raised to the power x plus c dash. So in many forms, we may leave our final answer as the required solution of the given differential equation, mod y minus 1 is equal to minus x plus c, or, so the fourth question is sec square x tan y dx plus sec square y tan x dy is equal to 0. So here transposing this term to right hand side, on the left hand side we get sec square y tan x dy, sec square y tan x dy is equal to minus sec square x tan y dx. Now transposing tan y to left hand side and tan x to right hand side, we get sec square y over tan y. When we transpose tan y to left hand side, it goes in the denominator. Dy differential operator is equal to minus sec square x was already there on the right hand side, and we transposed tan x from left hand side to right hand side, so it goes in the denominator. So tan x dx as the differential operator. Now obviously this is variable separable form. So now in this step we have to integrate both sides. We get integral sec square y upon tan y dy is equal to minus integral sec square x upon tan x dx. Obviously here we may assume tan y as u and tan x as v. Now here if we differentiate this equation with respect to y, we get sec square y dy is equal to du, and if we differentiate this equation, we get sec square x dx is equal to dv. So by this substitution, this equation becomes integral 1 over u du is equal to minus integral 1 over v dv. Now proceeding from this step, on the left hand side we get integral 1 upon u du. So integral of 1 upon u with respect to u will be log u on the right hand side minus integral of 1 upon v with respect to v will be log v. Here mod v is understood. Whether we write here modulus or not, it is considered to be modulus because log is not defined for any negative number. So on the left hand side we have log u. The integral of the right hand side is minus log v and plus constant of integration should also be taken as log c, because if integrating an equation we have all the terms in the same format, so the constant term should also be taken in the same format. So log u. Now transpose log v to left hand side, it becomes plus log v. On the right hand side we are left with log c. So log u plus log v by logarithmic property may be written as log u into v is equal to log c. So it implies that uv is equal to c. Now by our substitution, tan y is equal to u and tan x is equal to v. If we substitute here the value of u and v in terms of x and y, we get tan y into tan x is equal to c, or tan x tan y is equal to c, and this is the required solution of the given differential equation. So the fifth one is e raised to the power x plus e raised to the power minus x dy minus e raised to the power x minus e raised to the power minus x dx is equal to 0. Transposing this term to right hand side, we get on the left e raised to the power x plus e raised to the power minus x dy. On the right hand side, we get e raised to the power x minus e raised to the power minus x dx. Transposing this term, that is this bracket, to right hand side, we get dy is equal to e raised to the power x minus e raised to the power minus x upon e raised to the power x plus e raised to the power minus x. So this is variable separable form, so integrating both sides we get integral 1 dy is equal to integral e raised to the power x minus e raised to the power minus x upon e raised to the power x plus e raised to the power minus x dx. Now here y integral of 1, and here if we substitute e raised to the power x plus e raised to the power minus x as u, so differentiating this we get e raised to the power x minus e raised to the power minus x dx is equal to du. The right hand side of equation becomes integral 1 upon u du. Proceeding from this step, y is equal to integral of 1 upon u du will be log u and plus c as the constant of integration. Substitute the value of u, that is e raised to power x plus e raised to power minus x. From here we get log e raised to the power x plus e raised to the power minus x plus c. Now the sixth one is dy upon dx is equal to 1 plus x square 1 plus y square. So now in this equation, if we transpose 1 plus y square to left hand side and dx to right hand side, it becomes variable separable form, and transposing 1 plus y square from right to left, it is written as 1 plus y square dy is equal to 1 plus x square dx. Now integrating both sides, we have 1 upon integral 1 upon 1 plus y square dy is equal to integral 1 plus x square dx. So integral of 1 upon 1 plus y square dy is tan inverse y, and integral of 1 on the right hand side is x, and integral of x square will be x cubed upon 3. C as the constant of integration, and this is the required solution of the differential equation. Seventh one is y log y dx minus x dy is equal to 0. So first we need to transpose x dy to right hand side. We may write it as y log y dx is equal to x dy, or we may write it as x dy is equal to y log y dx, or transposing y log y to left hand side and x to right hand side, this equation may be written as 1 over y log y dy is equal to 1 over x dx. Integrating both sides now. Integrating both sides, we get integral 1 upon y log y dy. On the right hand side, we get integral 1 over x dx. So here this is quite simple. This is integration by substitution format, where we need to assume log y is equal to u, implies that differentiating both sides of this equation, we have 1 over y dy is equal to du. So by this substitution, 1 upon y dy becomes du, and log y is substituted as u. So simply we get integral 1 upon u du, and on the right hand side we have integral 1 over x dx. Integrating, we get log u is equal to log x plus log c. because all the terms are coming in the format of log, so constant of integration should also be taken in the same format. Log u is equal to log x plus log c may be written as log cx by the property of logarithm. Now proceeding from this step, log u is equal to log cx. Both sides log may be eliminated and we may write it as u is equal to cx. Now finally we have to write down the value of u in terms of y. According to our substitution, u is equal to log y. So here we write log y is equal to cx. So it implies that using the definition of log, y is equal to e raised to the power cx. Now the eighth sum is x raised to the power 5 dy upon dx is equal to minus y raised to the power 5. So here first we have to transpose y raised to the power 5 to left hand side and x raised to the power 5 and dx to right hand side. We get 1 upon y raised to the power 5 dy on transposition, and on the right hand side we get minus 1 upon x raised to the power 5 dx. Or we may write it as y raised to the power minus 5 dy is equal to minus x raised to the power minus 5 dx. Integrating both sides, we get integral y raised to the power minus 5 dy is equal to minus integral x raised to the power minus 5 dx. Integral of y raised to the power minus 5 dy, integral of y raised to the power minus 5 with respect to y, that is y raised to the power minus 4 upon minus 4 is equal to here minus an integral of x raised to the power minus 5 with respect to x, that is x raised to the power minus 4 upon minus 4 plus c, constant of integration. So multiplying both sides by minus 4, we may write it as y raised to the power minus 4 is equal to minus x raised to the power minus 4 minus 4c. Or we may write 1 upon y raised to the power 4, transposing this to left hand side, plus 1 over x raised to the power 4 is equal to minus 4c. So this is the final solution of the given differential equation. The ninth sum is dy upon dx is equal to sine inverse x. So this equation may be written as dy is equal to sine inverse x dx. Integrating both sides, we get integral 1 upon dy is equal to integral sine inverse x dx. Integral of 1 with respect to y is obviously y is equal to, on the right hand side we have integral sine inverse x dx. So inverse trigonometric function may be integrated by integration by parts. So we should write sine inverse x as sine inverse x into 1 dx, and considering sine inverse x as the first function and the 1 as second function, we may integrate it using integration by parts. So first function as it is, second function is 1 integral with respect to x is x, minus integral as a whole. Differential of first, that is sine inverse x differential, will be 1 over under root 1 minus x square, and integral of the second one, that is x dx. Now we should assume 1 minus x square as u. So differentiating, we get minus 2x dx is equal to, transposing minus 2 to right hand side, we get x dx is equal to minus 1 upon 2 du. So this equation becomes y is equal to x sine inverse x. Remember, this substitution is made only for this integrand, so this term should be written as it is, x sine inverse x minus integral x dx becomes minus half du, and this is taken as u. So 1 upon under root u into minus half. Now proceeding from this step, we have y is equal to x sine inverse x. This minus half is taken out of integral because this is constant coefficient. So minus into minus becomes plus half integral. The root u in the denominator may be written as u raised to the power minus half in the numerator du. Y is equal to x sine inverse x plus half. Integral of u raised to the power minus half is u raised to the power plus half upon plus half plus c. So this 2 is cancelled by this 2, and y is equal to x sine inverse x plus u raised to the power half is left, and u raised to the power half may be written as under root u plus c. Now finally, the value of u, that was 1 minus x square. So x sine inverse x plus under root 1 minus x square plus c. And this is the required solution of the given differential equation. So the 10th sum is e raised to the power x 10 y dx plus 1 minus e raised to the power x sec square y dy is equal to 0. Transposing this term to right hand side, we get 1 minus e raised to the power x sec square y dy. On the left, the right hand side, we have minus e raised to the power x 10y dx. Now for separating x and y, we need to transpose 10y to left hand side and 1 minus e raised to the power x right hand side. So on the left hand side, we get 10y dy is equal to minus e raised to the power x divided by 1 minus e raised to the power x dx. Now sec square y upon 10y dy. Taking minus common out of this bracket, this minus becomes plus, and we may write this expression as e raised to power x upon e raised to the power x minus 1 dx. Now integrating both sides, integral sec square y upon 10y dy is equal to integral e raised to the power x upon e raised to the power x minus 1 dx. Now substituting 10y as u, e raised to the power x minus 1 as v. Differentiating this equation, we get sec square y dy is equal to du. Differentiating this equation, we get e raised to the power x dx is equal to dv. So this equation becomes integral 1 over u du. On the right hand side, it becomes 1 over v dv. So integral of 1 upon u with respect to u is log u, because integral of 1 upon x with respect to x is log x. Similarly, integral of 1 upon v with respect to v will be log v. And constant of integration should also be taken in the same format, that is log c. Log u as it is, and log v plus log c may be written as log c into v by logarithmic property log m plus log n is equal to log m into n. And now eliminating log from both sides, we may write it as u is equal to cv. Now putting the value of u and v, u was substituted as 10y, so we get 10y is equal to c, and v was substituted as e raised to the power x minus 1. So e raised to the power x minus 1. So this is the required solution